We had 9 questions for homework last night on page 553. 3 of them we need to go over today, 5, 8, and 9b. So let's take a look right away at question number 5. It says if vector arrows can represent electric field at a point surrounding a charge, which of course they can, because vectors are quantities with both magnitude and direction. So of course an arrow can represent the electric field. Identify 2 ways that the vector arrows shown below represent differences in the electric fields around the 2 source charges. What's one difference? Both of them are actually staring us in the face, but sometimes the ones that are staring us in the face are the hardest ones to find. What's one difference? Yeah, the direction is different. The direction is different. You can look at it and say this one is pointing to the left, this is pointing kind of diagonally. I would probably tackle the direction in a slightly different way and say this one is toward the producer, this one is away from the producer, right? We're always toward a negative producer, always away from a positive producer. So the direction is one difference between these two. What's another difference between them? Yep. Yeah, one's longer than the other. What does that mean? If these are drawn to scale, that is, then what does it mean when one's longer than the other? No, not a greater force. Greater, you almost said it there, and then you kind of stopped. Magnitude, yeah. If it's a bigger arrow, a longer arrow, then it's a greater magnitude. So the magnitude and the direction is different. Think about what the definition of a vector is. Something with both magnitude and direction. Well, what do you think the 2 differences are going to be? The magnitude's different and the direction's different. The 2 properties of a vector. All right, let's take a look at number 8 now. This one says a small test sphere. Somebody asked me yesterday, this class or the other class, I'm not sure, what a test sphere is. What's a test sphere? Well, sometimes if we read a little bit further and we kind of look at the context, sometimes we can figure out what a test sphere or some other definition means. A small test sphere with a negative charge of 2 microcoulombs, 2.5 microcoulombs, experiences an electrostatic force of this value in its place at this value. Tell me what a test sphere is now. After reading that sentence, tell me what a test sphere is. An experiencer, right? Our word for a test sphere is an experiencer. Okay, that's my word, the word experiencer. Usually you see test sphere, actually. I like the word experiencer better because I think that describes better what it is. It experiences the field. But in the end, this is exactly the same thing. Experiences this force when it's placed this far from another larger sphere. What's the magnitude and direction of the electric field at this point? What's the magnitude and the sign of the charge on the larger charged sphere? I think this is a great question. I think it's a great question because I think it requires a good, solid understanding of the mathematics of electric fields. In addition to that, I think it requires an understanding of signs of charges and directions of fields. I think it's just a good, solid question for us. I think the way that we should tackle this is probably draw a picture. Right, draw a picture. But before we do that, I'm going to take out the red pen and start circling things. We got a negative charge. We got 2.5 microcoulombs. Okay, let's draw it out now that we have that circled. We have a small test sphere. We're going to make it negative 2.50 microcoulombs. It experiences an electrostatic force. We're going to say a magnitude. The magnitude of it is 5.10 times 10 to the minus 2 newtons. It's placed 0.0400 meters away from a larger charged sphere. All right. If we're dealing with fields, something's going to be the producer, something's going to be the experiencer here. Tell me which one, the small one or the big one, is the producer? Which one are we treating as the producer here? Yep, the big one, yeah. What do we know more about then? The producer or the experiencer? The big one or the small one? I think it's pretty clear we know more about the small one here, right? So if we know more about the small one, the small experiencer, then let's use the experiencer equation. E is equal to F over Q. We know the force. It's 5.10 times 10 to the negative 2, or at least we know the magnitude of the force. Divided by the charge. We're going to drop the sign of the charge. We always do when we're plugging into an equation. 2.5 times 10 to the minus 6 coulombs. I'm not going to forget that 10 to the minus 6 because I circled it, right? Now, if it was me who made up your data sheet and it wasn't, then I would have put absolute value signs around this just the same as we did around the electric field around a producer. Why? Well, because this equation doesn't tell us the direction of the field any more than the producer equation does. So if we're only getting the magnitude from the equation, it really should have absolute value signs. Your data sheet doesn't have it as absolute value signs. It's not a big deal. Okay? But in the end, just remember that this equation will not give you the direction. You've got to figure that out some other way. We can get the magnitude this way, though. 5.1 divided by 2.5 is going to be 2.04 times 10 to the 4 newtons per coulomb. Now, what about the direction? Hey, good. We got the magnitude. Great. What about the direction? Here's where we got to look a little bit beyond the mathematics. We have an experiencer that has a negative charge. We know that it experiences a force that is toward the producer. So we're going to say the force is toward the producer. Actually, let's draw that force over here. If it's attracted to the producer, if it experiences a force toward the producer, what do we know about the field? What do we know about the direction of the electric field, Bryce? Left or right? No. The electric field is going to be to the left. We want to find the magnitude and the direction of the electric field. Here's the magnitude, here's the direction. But why? Why is it to the left? How did I know that? We talked about this the first day we talked about electric fields. We define electric field direction as the direction that a positive particle would move if placed in the field. Well, if a positive particle will move one way when placed in the field, then a negative particle must move the opposite way. So positives always experience a force in the direction of the electric field. Negatives always experience a force opposite to the direction of the electric field. If the force is to the right, and this is a negative particle, then the field must be to the left. Make sense? We're going to verify that in just a moment, not in terms of fields, but in terms of Coulomb forces or electric forces. And you'll see what I mean by that in a sec. B says, what's the magnitude and the sign of the charge on the larger charge sphere? So what's the magnitude of the charge of the producer here? I'm probably going to use the producer equation for this. Turn around and solve for Q here. It becomes E times R squared over K. E is the same value as I just got, right? If the field experienced by the little guy is 2.04, then what was the field produced by the big guy? Had to be 2.04, right? Where else would it have come from? We're going to say 2.04 times 10 to the 4 times the distance squared, 0.0400 meters squared, divided by the constant, 8.99 times 10 to the 9. I'm not sure what that number works out to be, but you can find that, right? That's pretty easy mathematically to find at this point. Positive or negative, though? Yep. Why do you say positive? Okay, good. So there's a couple ways that you can kind of tackle this. One is exactly what you just said, Bryce. Okay, it's an attractive force. If that's a negative particle, and we were told that, then this thing over here has to be positive, because the only thing that's going to attract a negative is that positive, right? Good? The other way we can look at it now is to say, hey, look, we just found the electric field caused by this big producer to be to the left. Well, if the electric field is to the left, away from the producer, then the producer must be positive, right? Either way you can look at that. Yep.
I solved mine a different way.
Okay, how'd you do that? Oh, I think, you know what? Hold on. I think you know, was it with, no, never mind. You go ahead.
Oh.
Go ahead.
I did it with the electrical force.
Yes. Yeah, that's absolutely correct. Alex, instead of saying, using the field equation for the experiencer, getting the field, and then subbing that into the producer equation, instead of doing that, Alex said, for the second question, right? KQ1, Q2 over r squared. We're looking for, what are we looking for there? Well, let's call this Q1 and let's call this Q2, two separate charges, right? Experiencer, producer. We're looking for Q2 there. Well, we know the force. We know K, we know Q1, and we know the distance. Why couldn't we do that to solve for Q2? It's absolutely valid. Okay, if you have two charges a certain distance apart and you're dealing with the electric force, that's absolutely valid. Just as valid as what I did. Okay, what I want to show you here, Alex, is real quickly, since you brought it up, I want to set these two equal to each other with no numbers. So in other words, the electric field experienced by whatever is equal to the electric field that's produced by whatever it is that caused this. In other words, F over Q1 equals KQ2 over R squared. Rearrange this. What do we end up getting? All right, if you combine your two electric field equations, then you get Coulomb's law. It's not a coincidence that those all work, right? I'll tell you this from the beginning of Physics 20, and we'll continue to tell you this for the rest of eternity in physics. If you do something that's valid, and I did something that was valid, and you did something that was valid, we just did different things. If you do something that's valid, assuming you don't make a silly mistake somewhere, you're going to get the right answer. It doesn't have to be remotely close to my way. I was telling my grade 11s here, last week, my nephew is taking geophysics at U of C. He's his first year doing a physics course, introductory physics course at U of C. He gets this crazy hard question, and he's struggling with it. Can't get the answer, can't get the answer. So we're FaceTiming each other, and he gives me the question, texts me a copy of that question, and I'm working on the question, and I do it in this challenging question, but I do it in this way where, I won't explain it here now. Tricky question though, really tricky question. Anyways, he looks at it and says, yeah, okay, that kind of makes sense. Let me show you what I did, okay? So he shows me what he does, and I'm like, that should work. That should work. Well, I'm not sure what you did wrong. So we go through it. He made a silly mistake, but it was completely different than the way that I did it. In fact, his way is probably better than the way that I did it. It was completely different though. But they both work as long as you don't make a silly mistake. Because as long as you're doing something that's valid, then it should be good. Okay? All right, next question, number 9, 9B it was. This question was, talk about challenging questions. This is a challenging question. It's not quite as ugly as the one you had last week, though, with the electric forces. Remember that one? Where does the middle charge have to be so that the net force is 0? Why isn't it quite as ugly? Because it's almost the same. Because we've pretty much done it before, right? It's still hard, but it's easier than when we see it for the first time. We got two charges here. This negative charge right here is to the right of the other one, 3.00 times 10 to the minus 6 coulombs, and the distance is 1.20 meters. This charge is negative as well, and it's negative 2.00 times 10 to the minus 3 coulombs. This is 10 to the minus 3, actually, isn't it? Milli, not 10 to the minus 6. We want to find a point somewhere in here where the field strength would be 0. Well, we know that both of these produce a field. The first one produces a field to the left. The field has to point toward a negative producer. The second one's going to point to the right because the field has to point toward a negative producer. What do we know about the magnitudes of those two fields? We're trying to find the point where the field strength is 0. What do we know about the magnitudes of those two fields, Alex? They got to be the same. Okay, now, just because this point is partway between these two charges doesn't guarantee the fields will be the same. But if we're trying to find that point where the field strength is 0, then the opposing fields have to be the same, equal and opposite. We're going to say that E1 equals E2, or at least we're going to say the absolute values of them are going to be the same. The magnitudes are going to be the same. Remember the last time we set force equal to force, set field equal to field? KQ, we'll say KQ1 over R squared equals KQ2 over, what's the distance between the second charge and that point X? Good, 1.2 minus R. Not R, right? Because that's this distance right here. Or rather 1.2 minus R. Okay, simplify this a little bit. K's cancel. Q1, 2 over R squared equals 3 over 1.2 minus R squared. What did I do there? Yep, Bryce? Yeah, if you get a 10 to the minus 3 on both sides, cancel it. You don't have to. You can leave it in there if you want, but it just means more entries into your calculator, right? Let's try to make this a little tidier. Take the 1.2 minus R up by multiplying. Now let's take the 2 down by dividing. So 3 divided by 2 is 1.5. Square root both sides. You do whatever you want to both sides. Probably makes sense to square root it though. 1.2 minus R equals, what's the square root of 1.5? 1.2247, thank you, James. R, right? Because we get rid of the square there. Let's take the minus R to the right side by adding. I get 1.2 equals 2.2247 R, right? 1.22 plus 1 is 2.22. Now R is 1.2 divided by 2.22, 0.5 something, 0.6. I don't remember what that was. We get 0.55 meters. Now, go back to the original diagram here. So it's 0.55 meters from the first one. How far is it from the second one? 0.65. Does it make sense that it's further from the second one than it is from the first one? It's closer to the first one? Yeah. How come? Why does it have to be closer to the first one? Why does the distance between that point and the first one have to be smaller? Right. The value of the first charge is smaller, which is going to make the field strength, all other things being equal, smaller. In order to get the field the same, we have to decrease the distance and increase the distance in the other one. Got it? I'm going to take a look at a multiple choice question now as practice. Question number 50. Have a look at that from your worksheet booklet. We'll take a look at it as a group in about 1 minute. 50 says, the intensity and direction of the electric field produced by an alpha particle at a distance of 5 times 10 to the negative 11 meters from the particle is what? Clearly an electric field problem, right? Okay, we think about what the concept is. It's electric field. What do we see in here? What do we see in here that can lead us astray? In other words, what should we circle with a red pen? Yep. Okay. Okay. It's a producer. I'm not sure if I'm going to go red pen on that. Okay, but it's definitely worth noting, right? It's a producer. So we're probably going to end up using that producer equation. We know something about the producer. Producer equation is probably going to work for us. What's the thing in here that might lead to a silly mistake? It's an alpha particle. What are we used to using? Something like a proton or electron, right? So it would be so easy to make the charge of this 1.6 times 10 to the minus 19 as opposed to 3.20 times 10 to the minus 19, which is what the alpha particle is. All right, let's figure out what this is now. We got KQ over R squared. Where do we get that charge, by the way? 3.2 times 10 to the minus 19. Where do we find that? The easy answer is on your data sheet, right? That's the easy answer. Okay. So, but on your data sheet, I don't know, when I look up the charge of an alpha particle, it says 2e. How do we interpret that as 3.2 times 10 to the minus 19? Right. It's 2 times the elementary charge, which makes it 3.2 times 10 to the minus 19. All right, good. R is 5 times 10 to the minus 11. Don't forget to square that. Hey, if you do, guess what you get? 5.8 times 10 to the 11. If you forget to square it, the answer you get is there. Don't make a silly mistake because they're going to account for that. If you don't forget to square it, I believe you get 1.2 times 10 to the 12. Is that right? And the units would be newtons per coulomb, of course. All right, that doesn't tell us what the direction is. How do you figure out the direction? We're never going to get the direction from any of these equations, right? How do you figure the direction there? Go ahead. Good. So you got an alpha particle. It's positive. The field has to be away from it. So the answer is going to be D. Hey, I got a question for you. What if I put, just a little aside here, what if I put a little positive particle in that field right there? Where does it go? Which way does it go? Left, right, up, down? Morgan, which way is that going to go, that positive particle? Right here. Which way is it going to go, Luca? It's going to go away from it, right? It's repelled by this positive. Positives go or experience a force in the direction of the field, right? What if I put a negative particle right here? Where does it go? Where's that going to go, Tyler? It's going to go toward the positive, right? Negatives go opposite to the direction of the field. Positives experience a force with the field. Negatives experience a force opposite to the field. Hey, let's get rid of that picture and just generalize it even more here. We got an electric field that points to the right. I put a positive particle in that field. Which way is the force on that positive particle? Which way is the force on that positive particle? Quick. Yep. To the right. Positives experience a force in the same direction as the field. Oh, let's make it even harder here. Here's a negative particle that experiences a force downward. Which way is the field? Which way is the field on it? Good, because negatives experience a force opposite to the direction of the field. What caused that field? I don't know. Maybe it was a big positive down here. Maybe it was a big negative up here. Maybe it was both. Maybe it was two parallel plates. We don't know. Doesn't matter. If there's a field that points, if there's a force that points downward on a negative particle, then there must be a field that points upward. All right? Okay, let's try another one here. 51. Time to do this now. It says the magnitude of an electric field at a distance x from a point charge q is 8.3 times 10 to the minus 4. What does that sentence tell us? The magnitude of the field at a distance x from a point charge q is this. We have the value of an electric field. Is this charge, big Q, producing the field, or is it experiencing the field? Kathleen? Yeah, it's producing the field, right? If it was experiencing the field, then it would have to be at the point where the field is. Does that make sense? Like, you can't have a field right here and have a charge over here experiencing that field. If it's experiencing it, then it's got to be right there where the field is. Does that make sense? It's got to be a producer here. Now looks like we're changing the values of some of these things. The distance, we're changing the value of Q. We want to see what effect that has on it. That's a variable value changing question, right? The old, the new, right? Original field is KQ over R squared. You know, I hate it when they do things like this, right? The distance is X, the charge is Q. Don't get bothered by that. Call it little q, call it R. Okay, it's the same thing, just in more familiar terms to us. The original force, field is this. Its value is 8.3 times 10 to the minus 4. We're going to say the new field, after I make changes, is K times 1/4 Q over 3R squared. Becomes 1/4 over 9. 1/4 over 9 times KQ over R squared. And we know what that is, right? 1/4 over 9, by the way. You guys good with fractions? What's 1/4 over 9? Yep, Nathan? No. 1 over 36. Okay. You had the right idea. You just multiplied 4 by 9 wrong. That's all. And the value of kq over r squared is 8.3. Listen, if you're not sure how to divide fractions, do it on a calculator, okay? So it works out. I don't remember what the answer is, but it's going to have to be either C or D, right? Because you're not going to take 1/36 of that and get 10 to the minus 3 or 10 to the minus 4. Which one is it? D? All right. Let's do one more multiple choice, then we'll take a quick little break here, okay? This one's number 52, please, in your worksheet booklet. All right, question 52 looks kind of confusing, right? We got all these charges, 4 of them, kind of all over the place, and we want to find the field strength at point P. Had a good question. Somebody asked before we started doing this question. The question was, is it a positive particle at point P? Is it a negative particle at point P? Which is it? None of the above, right? At least we're not told any of the above, right? It could be a positive particle there, it could be a negative particle there, or it might be nothing there. We have to assume nothing because we're not told anything about an experiencer there. That's okay. At point P, we experience a field caused by number 3 to the right? It's away from the positive particle number 3. We experience a field caused by number 4 to the left, away from charge number 4. What do you know about the values of the magnitudes of those two fields? Go ahead. Yeah, they're going to cancel out. We know that because the distances are the same and the charges are the same. That's good news. Okay, that's good news. We can pretend those two charges aren't even there. That turns this problem from a two-dimensional problem where we have x and y into a one-dimensional problem where we just have y. Okay, good news. Let's deal with the other ones now. Charge 2 is positive. So at point P, the field caused by number 2 is going to be downwards, away from a positive. Charge 1 is negative. So we're going to have charge or field 1 pointing upwards toward the negative producer. Now, do we know if those two fields are the same? Well, the charges are different, the distances are different, so we don't know that those two fields are the same. If you actually calculate those two fields using kq over r squared, guess what you happen to find? They are the same. So they cancel each other out, and the field strength is therefore 0. Everything cancels. The other way you could look at this, say, look, E2, we're going to say is kq over r squared. E1 is going to be k times, well, the charge is 4 times the value of q2, and the distance is twice the value of it was for q1. 4 goes out in front, 2 squared goes out in front. Oh, look at that. E1 is 4 over 4 times the value of E2. So without doing the numbers calculation, you can still figure out that these two fields are equal and opposite, right?